Welcome to this presentation in the Electronica 2020 Embedded Forums, looking at microcontroller evolution from an interface perspective. My name is Martin Pilaski. I am working as Application Marketing Manager for Nexperia in Hamburg, Germany. This is the agenda for this presentation. First, we will look at who is Nexperia and what are our roots in the semiconductor industry. Next, we will have a look at the evolution of microcontroller technologies. Then I will introduce you to our logic device families and share some insights on voltage level translator technologies. Finally, I will provide a summary and give links for further reading. Before looking at microcontroller evolution, I want to look at the history of Nexperia, which ingredients were involved in making Nexperia the company it is today. Nexperia was founded in 2017 from the NXP standard products business, which was until 2006 part of Philips. Signetics, which was founded in 1961 and acquired by Philips in 1975, laid the foundation for what our logic business is today. Today, Nexperia is producing discrete devices, MOSFETs, and analog and logic ICs. In total, we ship over 90 billion products each year. Let's look at the microcontroller evolution. How have the microprocessors and microcontrollers developed over the years? In the chart on the right-hand side, you see the technology nodes as gray dots plotted against the feature size on the vertical and the time in years on the horizontal axis. Often overlapping with the technology nodes are the microprocessors, which are marked by the orange dots. It's no coincidence that the gray and orange dots overlap, as the microprocessors are often the driving force in the semiconductor process development. Roughly 7 years behind the technology nodes are the microcontrollers, shown in the teal dots. The absence of microcontrollers before 2007 does not mean that there were no microcontrollers, but rather that there was no sufficient data available to show them in this chart. From this chart, it becomes clear that microcontrollers follow the main semiconductor technology trend. The key requirements for microcontrollers today are low power consumption and high integration density. This can be achieved by small process features and low I/O and core voltages. In the context of shrinking I/O and core voltages, flexible options are required when interfacing between the controller and peripherals. This is exactly where Nexperia's logic products come into play. Even before the microprocessor evolution began, in the 1960s, it was state-of-the-art to build computing devices, mainframes at that time, largely out of logic devices. At that time, RTL, DTL, the first 7400 series, L, H, and S families of logic devices were introduced. With the first microprocessors coming up in the 1970s, also the logic products quickly expanded with more functions and more families. The 1980s saw the rise of the personal computers, giving the microprocessors a boost. In the logic world, higher performance families like AS, HC, HCT, AC, ACT were introduced. In the 1990s, desktop computing was well established. Laptops and mobile phones came up. The microprocessor vendors fought for higher clock speeds. Also for logic devices, still higher performance was required, but also power started to become an issue. Thus, the G family was introduced to serve the demand for higher speed, and LVC, LVT, and AVC families gave options for lower power consumption. Laptops started to dominate the PC business in the 2000s, and mobile phone shipments gained significant volumes. Supply voltages of logic devices were going down to match with the CPUs, and lower power devices were required for battery-powered devices. The AUP logic family was introduced. Mobile communication and computing, with smartphones and tablets, shaped the 2000 years. This asked for longer battery life. To fulfill the demand for logic devices with higher performance and ultra-low power, the AXP family was introduced. While the logic ICs started right at the core of the computing industry, over the years they moved more and more to the outside, mainly interfacing between the processors and their peripherals. Let's look at the logic products and the device families in more detail. What functions are implemented in our logic devices? Firstly, there's asynchronous logic with buffers, drivers, inverters, transceivers, logic gates such as AND and OR gates, decoders and multiplexers. Next is interface logic functions, voltage translators, level shifters. On the synchronous logic side, we have flip-flops and latches, frequency counters and dividers, shift registers, and some specialty logic functions. Additionally, our devices implement analog switches and multiplexers. This brings us to an overview of our logic families. The tables list all the important parameters like supply voltage, propagation delay, output drive capability, and standby current, both for high voltage and lower voltage logic devices. In this context, I just want to point out the LSF family, which for the high voltage part offers a very large supply voltage range from 0.95 to 5 volt. And for the low voltage side, the AXP family supports the lowest supply voltages down to 0.7 volt, perfectly ready for today's low voltage processors. Whenever an interface between different I/O voltages is required, voltage translators can be used. This table lists Nexperia's portfolio of voltage translator devices. The first two devices in this list, the AUP1T and the LV1T, operate only from a single supply voltage, which also defines the output voltage. As the inputs of these devices feature a low threshold voltage and are overvoltage tolerant, they can translate between voltages slightly lower and higher than their supply voltage. Both are available as standard single logic gate functions. The AUP-T family offers a supply voltage range of 2.3 to 3.6 volt with an input voltage range down to 1.8 volt. The LV-T family offers an even larger operating voltage range as it works from a supply voltage range of 1.6 to 5.5 volt with an input voltage range down to 1.2 volt. The AXP-T devices are 1 to 8 channel bidirectional transceivers with two supply voltages. The direction of data flow needs to be controlled with a direction signal. While the AXP-T devices require a signal to control the direction of data flow, the remaining 4 devices feature an automatic detection of the driving direction. The LSF devices work with the pass transistor as active element for level translation and work from 0.95 to 3.3 volt on VCCA side to 1.8 to 5 volt on the VCCB side. The NXS devices work with the pass transistor plus one-shot circuits operating from 1.65 to 3.6 volt on the VCCA side to 2.3 to 5.5 volt on the VCCB side. The NXP family operates with push-pull drivers plus one-shot circuits for VCCA of 1.2 to 3.6 volt and VCCB of 1.65 to 5.5 volt. The last device in this list, the NXS 0506, is a level translator dedicated for the SD card interface. After the brief overview of the logic device and voltage translator families, let's go into details on how the voltage translators work and what their properties are. Before we start to dive into the details of these 3 Autosense translator families, let's have a quick comparison. As mentioned before, the LSF translators work with one pass transistor per channel. In addition to the number of channels, every LSF device has a reference channel that is used to properly bias the other channels for the voltage translation. For LSF translators, external pull-up resistors are needed. These devices can be used on push-pull interfaces like SPI or open drain buses like I2C. The NXS translators extend the LSF design with one-shot circuits and high-side drivers to accelerate the rising edges and already include the pull-up resistors. The NXS devices can also be used for push-pull and open-drain type interfaces. The last family in this overview is the NXP family. It uses push-pull drivers and one-shot accelerators. The NXP translators can be used with push-pull type interfaces like SPI, I2C, serial UART interfaces. For the past transistor-based level translators, like the LSF family, it is important to understand that the level translation relies on enabling or disabling the transistor only by changing the driving side voltage of the transistor channel. A low voltage turns the transistor on and it subsequently drives the low on to the receiving side. A high level turns the transistor off and the receiving side is pulled high by the pull-up resistor. For this to work, the reference channel is needed to create the proper bias voltage for the gates of the other channels. All gates of the passed transistors are internally connected to the enable pin. The enable should be externally shorted to VREF-B and have a 200 kilo-ohm resistor towards the supply for the VREF-B side. For understanding how the translation works, the pass transistor can be thought of as back-to-back MOSFETs with common drain. This is however not the real implementation, especially the body diodes are not there in the real design. One downside of the LSF translators is that the speed of the rising edge depends on the size of the external pull-up resistors. As the minimum size is limited to reduce current consumption, the maximum speed for this architecture is limited. An improvement of this situation is achieved in the NXS translators. Besides the pass transistor, which is similar to the LSF translators, it features one-shot circuits and corresponding PMOS drivers that help accelerate the rising edges without jeopardizing the good features of the pass transistor, like support for open-drain buses. The NXS translators also feature internal pull-up resistors on both VCC-A and VCC-B sides, and an output enable to disable the active circuitry and disconnect the pull-up resistors in case of power down to prevent leakage. For the NXS translators, it is recommended to have the high voltage side connected to VCC-B. Let's look at how the translation for the NXS translators works in detail. First, we will look at the up translation where the low voltage side is driving. In case of driving a high, which causes a rising edge, the starting point is a low level. Here the pass transistor conducts, causing a stable low level on both sides. With increasing input voltage, the pass transistor switches off as soon as Vin exceeds the gate voltage minus the threshold voltage. Then, as Vin is roughly half the supply voltage, the one-shot circuits trigger and activates the PMOS transistor T2. This accelerates the rising edge at the output. After a short time, the one-shot circuit turns off and a stable high is maintained by the pull-up resistors. In case of driving a low level, resulting in a falling edge, both ports start with high levels. As the A side begins to drive a low, the pass transistor starts conducting when Vin drops below gate voltage minus threshold voltage, causing the B port to follow the input port to a low level. The downward translation with the B side driving works just the same way as the up translation. Let's have a look at the next Autosense translator family, the NXP translators. How does the driver architecture for these look like? It features two full push-pull output stages with one-shot circuits for both high and low side drivers. Additionally, there is a weak buffer with a 4 kilo-ohm output resistor to maintain the output level once the one-shot circuits have turned off the push-pull drivers. In this architecture, there is no more pass transistor, making it suitable for push-pull type interfaces. It is recommended to use the NXP translators with VCC-A as the lower power supply voltage. The parts can be activated with an output enable signal, which turns on the one-shots and the output buffers. How does the translation work in more detail? First, we will look at the up translation with the low voltage side driving. If a rising edge is detected, the one-shot circuit triggers the PMOS transistor T1 for a short time and switches off afterwards. In parallel to that, the weak buffer drives a high through a 4 kilo ohm resistor in order to maintain a stable high level after the one-shot circuit has turned off T1. In case a falling edge is detected, the one-shot mechanism triggers the NMOS transistor T2, and again the weak buffer drives the B port low, maintaining a stable low level after T2 has turned off. For the reverse direction, the downward translation, it works just the same way for the driver on the opposite side. There's one thing that needs to be observed with the NXP type driver architecture. In a steady state, with a steady high or low level, the buffer is driving any load only via a 4 kilo ohm resistor. One-shot circuits and the strong push-pull drivers are deactivated at this stage. Thus, in case of any external pull-up or pull-down resistor, the internal and the external resistors form a voltage divider network. For this case, the output voltage can be calculated from the value of the pull-up resistor and the voltage level it is pulled up to. Following the previous, more general-purpose type level translators, we now have a look at an interface-specific translator, the NXS 0506 for SD card interfaces. This device is intended for parallel-type SD card interfaces and supports clock speeds up to 208 MHz for the STR104 mode. On the host side, it operates with 1.2 to 1.95 volt supplies, and on the card side, it supports 1.8 volt and 3.3 volt operation from an external source. All card side pins are ESD protected up to 8 kV IEC 61000-4-2 system level. Also EMI filters to suppress higher harmonics from the output drivers, as well as pull-up resistors as they are required by the standard are integrated. The product comes in a small 0.35 mm pitch wafer level chip scale package measuring just 1.4 by 1.4 mm. It mainly targets future smartphone platforms. Let's have a look at a simplified view of the internal driver structure of the NXS 0506. The structure is similar to what we saw from the NXP translators before. As for the NXP translator, no control signal for the data flow direction is needed. The direction is automatically detected. The driver architecture operates with a strong low and a weaker high, plus a one-shot mechanism. During a rising edge, the one-shot circuit turns on the PMOS transistors T1 and T3 for a short duration, accelerating the low to high transition. For driving a low level, the NMOS transistors T2 and T4 are turned on. This concludes the look at the details of the level translator technologies, and we come to the summary. Looking at the microcontroller development, it is clear that they follow the main semiconductor trend of smaller process feature sizes and lower core and I/O voltages. Nexperia's logic products and voltage translators are well suited for today's submicron CPUs and microcontrollers with support for I/O voltages down to 0.7 volt. For further reading, I would like to point you to our newly released Logic Application Handbook. It's a design engineer's guide. It is made by engineers for engineers. It's meant to enable and support everyone to understand Nexperia logic products, their behavior, and give guidance on how to use them in a design. It covers many product features and application aspects. You can download it from nexperia.com/products/analog-logic-ICs. That's all for my presentation today. In case you have any further questions, please use the feedback methods provided by the Electronica Forums platform. I'm looking forward to your questions and feedback. Thank you for your time.